some vector identities on that same table, okay? For example, we talked about some of these earlier, the fact that the divergence of the curl of any vector field is always 0, or that the curl of the gradient of any scalar field is always 0. Right? And then there are some other identities also. I took this actually from the front cover of a textbook that we use for our upper division electricity and magnetism course. As you know, electricity and magnetism is one of the areas of physics where vector calculus is most applicable. Anyway, there was just one difference in notation on this sheet from what we use in class, and that's that when they talk about cylindrical coordinates, okay, so on this sheet that I'm handing you, they use S instead of R. Right? The variable that measures the distance from the z-axis, which we called R in cylindrical coordinates, on this sheet they use S instead. Presumably because they want to avoid confusion with the R in spherical coordinates. Because remember, the cylindrical R and spherical R are not the same. And also for the angle in cylindrical coordinates, they call it phi instead of theta. Right? So in class, we used R, theta, and z for our 3 variables in cylindrical coordinates. So on this sheet of paper, they instead use S, phi, and z, in other words. Okay? So again, presumably the first point here was to avoid confusion with the spherical coordinate R. And the second point, remember when we actually talked about cylindrical coordinates, we said the angle that we were calling theta is really more similar to the spherical phi than it is to the spherical theta. And so I think there's good reason to maybe call it phi like they do in this sheet that I've handed out. But anyway, just notice that we have those differences in notation between compared to what we're used to. I was trying to find a list like this for you that used the notation that we had used in class. In other words, R, theta, and z for the cylindrical coordinates. But I couldn't find a nice convenient list. Okay, so this is your list. And like I promised you before, you can use this sheet of paper during the exam. Okay, so if anybody didn't get this, if anybody came in late and didn't pick up a copy, make sure you get one. So you can use that during the exam. In addition, of course, to one 8.5 by 11 sheet of paper with whatever notes you want written on it. Okay? And so our test is coming up Monday. Did I post a practice test yet?
No, you have not.
Asked me about that. Okay, I'm sorry then. I will get that posted today.
I think you posted a list of topics. I thought I saw.
Oh, the study guide. Yeah, I guess that's what I promised you, not a practice test.
Oh.
Okay.
Test too.
Okay, let me see if I can find a practice test that will work. Okay, and post that. But I did post a study guide, which is basically just a list of topics. Okay? Okay, so, and did anybody not get the homework 5 that I handed out last time? I got one copy of it left. Okay, if anybody else needs a copy, it is available on Blackboard, of course.
Can we write on this as well? With
Sure.
Okay.
Sure. Okay, so anyway, last time we were talking a little bit about electricity and magnetism, in particular Maxwell's equations. And again, I'm not going to ask you anything explicitly about Maxwell's equations on the exam, but I wanted to just talk about them a little bit to give you a feeling for how some of this vector calculus stuff is used in physics. And so let me reiterate, we didn't quite finish this, so it's going to take about 10 or 15 minutes today to finish this up. So let me first reiterate by reminding you of Maxwell's equations. I'm going to write them both in differential form and in integral form. And I'm going to specialize to the case where we're located in a vacuum and not in some type of material. You might remember that the first, most general version of Maxwell's equations I wrote on the board yesterday, or last time, which were good in a material as well as in a vacuum, involved 4 different fields. Our familiar E and B fields, electric and magnetic fields, but also a D field and an H field, which were closely related to the E and the B field, respectively. In a vacuum, the relationship, remember the D field is just epsilon naught times the E field, and the H field is 1 over mu naught times the B field. So I can write, in a vacuum, I can write Maxwell's equations just involving the 2 more familiar types of fields. So anyway, if I do that, Gauss's law, which is normally considered the first one of Maxwell's equations, tells us that the divergence of the electric field is equal to a charge density rho divided by the constant epsilon naught. The second one, which is Gauss's law for magnetism, tells us the divergence of the magnetic field, the B field, is 0. The third one, which is Faraday's law, tells us the curl of the electric field is equal to minus the time derivative of the magnetic field. And the last one, which is the Ampere-Maxwell law, tells us that the curl of the B field is equal to mu naught times J, which J is the current density or current per unit area flowing through a surface, plus mu naught epsilon naught times the time derivative of the electric field. These time derivatives in both Faraday's law and the Ampere-Maxwell law describe the process of induction, right? That a magnetic field that changes with time produces an electric field, and an electric field that changes with time produces a magnetic field. Okay? Anyway, so these were the differential forms, and then the integral forms, well, for Gauss's law, the integral of the electric field dotted into an n hat vector and integrated over some surface S. N hat, as usual, is a unit vector normal to the surface pointing outward. This is a closed surface, so we can put a little circle on the integral sign to remind us of that. And so this is the flux, right, of the electric field, and this is equal to the enclosed charge. The charge enclosed inside of our Gaussian surface, which is the surface we're integrating over here, divided by epsilon naught. And remember the way we get from the differential form to the integral form? You can start with the differential form, integrate both sides over a volume, the volume enclosed inside of our Gaussian surface. The integral of the charge density over that volume gives us the enclosed charge inside the surface. And the integral of the divergence of E over that volume, we can rewrite that using the divergence theorem as this flux integral over the surface. Similarly, if we take Gauss's law for magnetism, integrate both sides over a volume again enclosed inside of a Gaussian surface, well, the right-hand side is still 0. On the left-hand side, the integral of the divergence of B over that volume, we can rewrite using the divergence theorem as a magnetic flux. In other words, B dot n hat integrated over this entire surface. So that integral is equal to 0. Right? So that's the integral form of the second one of Maxwell's equations. For the third one, the integral form tells us that the integral of E dotted into dr, infinitesimal displacement vector, and integrated then around some closed path we'll call C. That is equal to minus the time derivative of a magnetic flux. B dot n hat d sigma integrated over the surface enclosed inside of the closed curve C. That's an open surface, not a closed surface, so I don't put a circle on that integral side. And again, the way we get from this one to this one, we take the differential form, we dot both sides into n hat, and then integrate over d sigma over a surface S. The right-hand side pretty directly then gives us this. We just change the order of the integration and the differentiation, and that's it. On the left-hand side, we use Stokes' theorem to rewrite the integral on the left-hand side as this line integral. Okay. Similarly, for the fourth one, the Ampere-Maxwell law, we again dot both sides into n hat and integrate over an open surface. On the left-hand side, we use Stokes' theorem to rewrite that integral as the integral of d dot dr. Again, integrated around some closed surface. That closed surface forms the boundary, or closed curve, I'm sorry, forms the boundary of the surface. We're going to have the integral over on the right-hand side. On the right-hand side, we have mu naught times the enclosed current, I. That's the sort of Ampere's law part of it. And then the Maxwell correction, which leads to this second term, which again describes the process of induction, a changing electric field producing a magnetic field. Once we do the manipulations, the integration we're talking about, this will turn into mu naught epsilon naught times the flux of the electric field over the surface S that is again bounded by the curve C. Okay, so again, those were Maxwell's equations, and we looked at one simple example last time involving electricity. Namely, we looked at a point charge, let's say a positive point charge. We figured out the electric field set up by this point charge. The point charge is Q at distance r away. The electric field, of course, is Q over 4 pi epsilon naught r squared, and it's in the r hat direction. In other words, it points radially outward. And we verified, or actually, I mean, this, I guess you could say this is how we derived the electric field, is to use Gauss's law. But of course, since we clearly have a charge, the divergence of this electric field is non-zero. You can see that just from the picture. The field lines are diverging from the charge itself, right? Their tails are attached to it. So clearly, remember we talked a little bit about what vector fields whose divergence is equal to 0 or not equal to 0 kind of look like. Clearly this has a non-zero divergence. The curl, however, is 0. You can kind of see that from looking too. You can see that basically there's no swirliness to this pattern of electric field lines. So again, that was the example we looked at last time. I want to look at just one more example today to finish up our discussion of electricity and magnetism. And that is, let's think about a long straight wire carrying a steady current. So steady current I in this wire. Imagine the wire is stretched out along the z-axis. And because of the geometry of the situation, we are going to want to use cylindrical coordinates. So anyway, right, so here's our wire. That's supposed to be straight. I know it doesn't look like it, but that's just a failure of my artistic abilities. We expect the magnetic field, right? We know that moving charges, that like the moving charges that make up this current, set up a magnetic field, right? All magnetic fields are ultimately caused by moving electric charges. And the magnetic field, we know from our discussion of magnetic fields back from Physics 222, or whatever introductory physics course you had. We expect it to be in the theta hat direction. In cylindrical coordinates, I'm using r, theta, and z instead of the s, phi, and z that was used on the sheet I handed out to you. And I noticed a couple people have drifted in late. So if you didn't get it, let me remind you to pick up one of these sheets of paper. I promised you a list of the vector operations, curl divergence, gradient, and Laplacian in the 3 major coordinate systems. I said you would be able to use that on the test. This is that sheet of paper, okay? So pick one up. Before you leave, you're going to want to bring it to the test with you. And as I remarked at the beginning, that sheet of paper uses slightly different notation for cylindrical coordinates than what we used in class. Okay, so just a caution. They use s instead of r and phi instead of theta, okay, for the cylindrical variables. So I'm sticking with the notation here that our book uses, which is, again, theta, not phi, for the angle. We expect the magnetic field lines, remember the magnetic field lines for a long straight current carrying wire like this, make circles around the wire, right? The wire runs through the center of the circle and perpendicular to the plane defined by that magnetic field line. And the magnetic field line, remember, has an arrow on it whose direction is related to the direction of the current in this wire by the right-hand rule. And if I put my thumb in the direction of the current, my fingers circulate in the direction of the arrows on the magnetic field lines. And so that points in the theta hat direction, right? So we expect B to be in that direction. And as usual with Maxwell's equations, it kind of helps us do integrals like maybe this one here if we know the direction of B to begin with. Okay? So anyway, so let's use, right, if we number Maxwell's equations like this is the same numbering we used last time. We can use equation 4, right, the Ampere-Maxwell law. Let's use the integral form of it. And let's choose our Amperian loop, which is this path we call C, the integral here on the left side. Let's choose that path to be a circle of radius r centered on the z-axis. And in a plane perpendicular to the z-axis. So in other words, we'll choose it to be a circle that basically runs right along one of these magnetic field lines. Okay? So our Amperian loop, if we traced it out in dashed lines, would just be right on top of the field line that I already drew here, right? At a distance r from the axis. And we're going to go around it in the same direction as the magnetic field. When we do the integral on the left-hand side of here. Okay? So then the integral of b dot dr around that closed curve C. Well, dr is an element of length as we go around the circle, right? So think of our dr as a little infinitesimal vector just pointing in the direction of the arrow, little piece of that circle. That's in the same direction as B, so the dot product of B and dr just gives us the product of their magnitudes. And then we use the argument that we expect that the magnitude of B is the same everywhere along the circle because by symmetry, we're at the same distance from the wire at each point as we go around that circle, so there's no reason to think the field is stronger or weaker at any point along this path than any other point. That means we can pull the B out in front. And the integral of dr around this path C just gives us the total length around the path. Well, we're going around a circle of radius r, so the length as we go around is the circumference 2 pi r. So the result of this is 2 pi r times the magnitude of B. Okay, so that's the integral on the left side of the Ampere-Maxwell law. The right side, well, the enclosed current is the current that pierces the surface. Imagine think of this Amperian loop as maybe some like a wire loop that you dip in soap film or something. When you pull it out, there's going to be a membrane of soap film stretching across, right? And the enclosed current means any current that is piercing that membrane and going through it, or going through the interior of the loop. Well, clearly the current in the wire is doing that, so the enclosed current is just I, the current in our wire. Okay? So that's for the first term on the right-hand side of the Ampere-Maxwell law. For the second term, whoops, I forgot a time derivative in the second term. Okay.
Yeah, you did.
Right, because there was a time derivative here, and that remains there when I do my manipulations. Anyway, in this situation, the second term on the right-hand side is going to be 0. Because we have no electric field, right? There's no net charge in this wire, right? We have moving charge carriers, but the wire as a whole is electrically neutral. So the electric field is 0. So, of course, the time derivative of the electric flux is also 0. Okay? So in this case, the Ampere-Maxwell law tells us that the integral on the left-hand side, which we've evaluated and found to be equal to 2 pi r times b, is equal to, on the right-hand side, we have mu naught times the enclosed current I, and the second term on the right is 0. Right? So this is it. So we can solve for b, and the magnitude of b will then be mu naught I over 2 pi r. And if we want to complete our answer here, of course, to specify b completely, we have to specify its direction as well. And as we've already noted, it is in the theta hat direction. And we kind of assumed that b was in the theta hat direction because we kind of already knew it. But I do want to point out, it is possible to show that b is in the theta hat direction. In other words, if we use spherical coordinates, b sub r and b sub z are both 0. And b sub theta, right, that's the coefficient of theta hat, so that's the mu naught I over 2 pi r. It is possible to show that b sub r and b sub z are 0 by picking an Amperian loop of a different shape than the one that we did. It's just a little bit tedious to do it. It's not quite as easy as what we did here, of course. It's easier to just say, well, we already know that this is true. But it actually can be proved. Okay? So we got this from the Ampere-Maxwell law, but notice that there is another one of Maxwell's equations that also involves the B field, namely equation 2, Gauss's law for magnetism. So maybe we should check that that still holds also. Right? So in cylindrical coordinates, the divergence of B, let's check the differential form of Gauss's law for magnetism. Okay, so that tells us the divergence of B should be 0. So let's double check that the divergence of this B that we just found is 0. So in cylindrical coordinates, the expression for divergence, you could read that off the sheet I just handed out. Again, remember they use S instead of R on the sheet, but if we switch back to R notation, divergence is 1 over R times the derivative with respect to R of R times B sub R. plus 1 over r times the derivative of b sub theta with respect to theta, plus the derivative of b sub z with respect to z. Well, in our case, b sub r and b sub z are both 0, so that's going to make that term 0 and this term 0. And this term, well, b sub theta is mu naught I over 2 pi r, but that doesn't depend on theta, so that term is 0 also. So clearly, right, the divergence is 0. So Gauss's law for magnetism is satisfied for this magnetic field. So just the final comment then to sort of compare that to the situation we described here. Let's imagine you put your eye above this wire up here and you were looking down on it like that. Right? The current would be coming out of the board towards you. It's indicated by this dot. And the magnetic field lines would be going in circles like this, centered on the wire, with arrows on them in this direction. Again, that's related to the direction of the current by the right-hand rule. Okay? And clearly looking at this, you can see that the curl of B is non-zero. Right? There's clearly a swirliness to this pattern. Right? Remember the test we talked about last time. Imagine if this were water flowing in a pattern like this and you put down a little paddle wheel somewhere, would it turn? Right? Well, clearly it would. Right? That pattern looks like a vortex. Right? And water is just swirling around like this. Clearly that paddle wheel will turn. So the curl is clearly non-zero, which is, of course, what the Ampere-Maxwell law tells us. Right? If you look at the differential form of it, the divergence is 0. Right? Unlike that electric field we drew over there, there's no divergence of magnetic field lines from a source, like from the charge here, or no, they're not coming in towards, like they would if that had been a negative charge. Right? They form closed paths. They close back on themselves. They don't end. Yeah?
So only if paths are closed do the divergence equal 0 and the curl equal not 0?
No, first of all, magnetic fields don't always close back on themselves. It's just this one that does. They can also extend to infinity.
I mean,
okay, but they can't end. Okay, for the divergence to be 0, the field lines would either have to extend to infinity or close back on themselves. Those are the two possible choices. In other words, they couldn't have ends that their tails are attached to or that their tips are attached to like this electric field did, right? This electric field had a divergence which was non-zero. If the field lines end or start anywhere, like they did here, then the divergence is non-zero. If they don't end or start anywhere, which means they either form closed loops or extend out to infinity in both directions, both their tails and their tips, then the divergence is 0, like was in this case. I'm not saying that that's related to the curl, though. The curl is related to just whether that, if you put down a paddle wheel, whether it would spin or not. So the curl is related to, not to whether field lines end or form closed loops or anything like that. It's related to this idea of the paddle wheel spinning if you set it down somewhere. Yeah?
If magnetic field lines went to infinity, would that mean it was a magnetic monopole?
No. In fact, a magnetic monopole would mean that they would end. Right? If there was such a thing as a magnetic monopole, let's say a north pole without a south pole, the magnetic field lines would point straight out away from it, just like the electric field lines do for a positive point charge. Okay? This would then have a non-zero divergence. In other words, if there were such things as magnetic monopoles, we'd have to go back and change Maxwell's equations. They no longer be true in the way we've written them. Gauss's law for magnetism, in particular, would look a little bit more like Gauss's law for electricity. Instead of the instead of the divergence of B being 0, the divergence of B would be equal to something like the density of magnetic monopoles. probably divided by mu naught or something like that. Okay? This and this would be more symmetric in appearance. Okay? And in fact, similarly, this and this would be more symmetric in appearance too. This term is kind of like that term, right? I mean, there are some constants that are different. Mu naught and epsilon, not here and not here. There's a sign difference. But otherwise, those are minor differences. Right? Otherwise, this term, except for E being replaced by B, this term and this term look very similar. But there isn't a term like this one on the right-hand side of equation 3. If there were such things as monopoles, there would be. Okay? There would be a term on the right side of equation 3 that described the flow of magnetic monopoles in the same way that this term describes the flow of the electric charges. Okay? So let me give you an example, though, where a field lines, I mean, these extend out to infinity, but they have ends at the tails, right? The tails are anchored to the monopole. An example where magnetic field lines do extend to infinity, because in this case they don't, they form closed loops instead, would be like, for example, a bar magnet. Right? If you have a bar magnet with the north pole at one end and the south pole at the other end, remember what the field lines do? Outside the magnet, they curve around like this. They come out of the north pole and into the south pole. And so that's why perhaps you think, you know, if you think of this as being a little bit analogous to the electric field lines set up by charges, electric field lines always point out from positive charges and in towards negative charges. And in a similar way, you could say these magnetic field lines point out from the north pole and into the south pole. So you're tempted to make an analogy between the north magnetic pole and a positive electric charge, and between the south magnetic pole and the negative electric charge. But the analogy is not really very good, because remember, this isn't the whole picture. These field lines don't end here. They actually go through the interior of the magnet like this to connect back up to the other end. So they do form closed loops. In that sense, they're similar to these. But if there's one right, a magnetic field line that goes right through the middle of the magnet like this, it's going to extend. It's going to extend from infinity down here and extend to infinity up there, right? So instead of forming a loop, it just keeps going and it extends to infinity. So again, magnetic field lines could do that too. So they either form closed loops or they extend to infinity, like that one down the middle there. Okay?
Oh, never mind. I was thinking in 2D planes. Never mind.
Okay.
I was going to say, wouldn't it just wrap around on the other axis? But then I was like, oh, right, three-dimensional.
Yeah. I mean, if there's some thickness to the magnet like this, it's true that a field line at the front would wrap around like this.
But in the very
and one
center
at
of the
back
magnet,
would wrap around the other way. But there still would be one right in the middle, right in the geometric center that just went straight through.
So where would, in practical application, where would that line extend to? So say if this was my magnet, that line would just go on.
Well, if your magnet is the only object in the universe, then it truly does extend to infinity.
Okay, so it just gets attracted to something
But,
else.
you know, given that there is other stuff in the universe too, then, you know, it could connect to another magnet somewhere or something like that.
Yeah.
Okay. To the Earth's magnetic field or
Yeah.
whatever. Okay, so anyway, that's the end of what we're doing with electricity and magnetism. Okay, so we're going to switch gears at this point. We're done with chapter 6 in our book. We're going to jump ahead to chapter 7, which is our second major topic for this quarter, namely Fourier analysis. Okay, and of course this will not be covered on our first midterm exam. And as I mentioned, I think I mentioned this on the first day, and I've reminded you a few of you about this since then. This will be a pretty quick topic compared to the vector calculus. Okay, we'll be done with it in 2 weeks, I think. So it means our second midterm, which will cover the Fourier analysis, will actually be fairly soon after our first one.
Is the Maxwell stuff on the first midterm?
I'm not going to ask you anything explicitly about electricity and magnetism, okay, on the midterm, or in fact, on any of the tests for that matter. So no, I'm not going to ask about Maxwell's equations or anything like that. I just mentioned this to hopefully give you a little better feeling for what the uses of this vector calculus stuff are. Okay? And hopefully a little more physical insight into for example, some of these sketches and whether, you know, we can just look at it and see whether a curl or a divergence is 0 or non-zero. Okay, so anyway, the very first thing I want to mention is just a reminder about complex numbers and some of the notation and so forth that we use to represent it. Okay, so we can write a complex number z in the form x plus I times y. X and y are both real. Okay? And I, of course, is the square root of -1, right? The basic complex number. So x is often called the real part of z. Write that like that. And y is often called the imaginary part of z, which we write like that. Right? The imaginary part of z is just the coefficient of I in this expression. Okay? And again, x and y themselves are both real numbers. The only thing that's complex on the right side there is the I itself. Okay? So, strange as it may sound, the imaginary part of a complex number is actually a real number. Okay? It's the coefficient of I, which is real. So anyway, we often represent complex numbers by using the complex plane. Okay? Sketch. So on the complex plane, what we have are it's a two-dimensional graph here. We have the real axis and the imaginary axis, right, as the horizontal and vertical axis respectively. So we can represent a number like this number z as a dot in the complex plane. And all we do is we start at the origin, and along the real axis we go over to a position x. And we go up on the imaginary axis to a position y. And that dot right there represents the number z. Okay? Its real part, which you do by projecting down to the real axis. Making a right angle right there will give you x, right? In other words, this distance right here is x. And this distance right here is y. And again, we go over a right angle like that to get there. Okay, well, another thing we often do on the complex plane is let's draw a line from the origin to the dot that represents our point z. Let's say that we define the length of that line to be r, and we say that it makes an angle theta with the real axis, okay, or the positive real axis. So anyway, we can see here from the complex plane if we use this right triangle right here, we can see that the cosine of theta would be the adjacent side, which is x, divided by the hypotenuse, which is r. In other words, x is equal to r cosine theta. And similarly, y is equal to r sine theta. Okay? Sine theta would be the opposite side, which is this side right here, which is the same as the y right there, divided by the hypotenuse r, and then you just rearrange that to get this equation.
That's the same as polar coordinates, correct?
Yeah.
Okay.
Yeah. And so you can, and also, and in fact, I'm going to write. In fact, there are two forms that a complex number can be written in. This one is sometimes called rectangular form or Cartesian form. Right, because we're basically using a Cartesian coordinate system, horizontal and vertical axis, right, for x and y. There'll be a polar form, which we'll write in a moment. Okay, I'm just kind of leading up towards it. The polar form will be in terms of r and theta. Okay, so anyway, if we want to let's say we knew r and theta and wanted to find x and y, right? This would be our way of doing it. If we wanted to go in reverse, if we knew x and y, but we wanted to find r and theta, well, r is the hypotenuse of this triangle, x is this side, y is that side, so by Pythagorean theorem, x is the square root, r is the square root of x squared plus y squared. And this angle theta is the arctangent of y over x. Right? In other words, the tangent of theta, which is the opposite side over the adjacent side, is y over x. Okay? So anyway, it looks like if I substitute these right here into the expression for z as x plus iy. Right, so for x, I'm going to substitute r cos theta, and for y, I'm going to substitute r sine theta. So it looks like I can write z as r times the quantity cosine theta plus I sine theta. I'm going to prove this to you in just a moment, but this is equal to e to the I theta. Okay? Again, I'll prove that to you in a minute. But anyway, if I substitute that in, I can write z as r e to the I theta, and this is the way of writing our complex number in polar form. Right? So this is rectangular form in terms of x and y, polar form in terms of r and theta. Okay? So anyway, let me prove this to you. It's actually very easy. And it's going to be important for you to remember this also.
Seems oddly familiar. Oddly familiar. I don't get it, bro. I think same numbers.
Okay, so e to the I theta. Sometimes we'll refer to this as a complex exponential, right? Because it has a complex number, I, in the exponent of this exponential. To write this expression, let's use the Taylor series. Right? E to the x for any number x. I'm hoping people have seen this before. Does this look familiar?
Yeah. Way too many times.
Okay.
I see them every day.
No idea what this is.
Hey, this is an infinite series. Right, the next term would be x to the 5th over 5 factorial and so forth. Everybody know what I mean by factorial?
Yeah.
Right? Okay, 4 factorial, for example, is 4 times 3 times 2 times 1. Right? Okay, right, so this is the Taylor series for the function e to the x. It's an infinite series, right? You can write a Taylor series for any function you want, right? You'll learn how to do that in math class at some point. So let's just write this for e to the I theta. In other words, write this out, but simply replace x by I theta. So this will be 1 plus I theta quantity squared over 2 factorial plus I theta quantity cubed over 3 factorial. I'm deliberately writing out quite a few terms of this, even though the pattern is obvious, because what happens in the next step may not be obvious unless you see the pattern in quite a few terms. Okay, so bear with me here while I put a few more terms. Okay, let's try to simplify some of this a little bit. In particular, let me write, when I have the I theta to some power, let me figure out what I squared or I cubed or, right? I squared is minus 1, right? Because I is defined as the square root of minus 1. So this term is really minus theta squared over 2 factorial. In fact, let me maybe make a list over here, right? I squared is minus 1. What's I cubed? I'm going to need that for the next term. Well, it would be I squared times another factor of I,
So it's
right?
negative I.
So it would be negative I. What's I to the 4th?
1.
Right? Because it's I cubed times yet another factor of I. So it's minus I times I, okay? Which is minus quantity I times I, and I times I, right? Or I squared is minus 1, so that's plus 1. I to the 5th is I, right? I to the 4th, which is 1 times one more factor of I. I to the 6th, minus 1, right? I to the 5th times one more factor of I, so I times I. I to the 7th, I to the 7th will be minus I, right? I to the 6th times one more factor of I. I to the 8th would be 1. You see the pattern? Right? I go through this pattern. Minus 1, minus I, plus 1, plus I. Minus 1, minus I, plus 1. The next one would be plus I. Right? I keep repeating those 4 numbers. Right? Okay, so let's use that over here. So here we got an I cubed. And we just concluded I cubed is minus I. So change that sign. This is minus I times theta cubed over 3 factorial. I to the 4th was plus 1. So this term is just theta to the 4th over 4 factorial. I to the 5th was I. So this term is I times theta to the 5th over 5 factorial. I to the 6th was minus 1. So this term is minus theta to the 6th over 6 factorial. I to the 7th was minus I. So this is minus theta to the 7th over 7 factorial, etc. Okay. Tell you what we're going to do in the next step. Some of these terms now have I's in them and some don't. Let's collect together all the ones that don't have an I, group them together in parentheses, and collect together all the ones with I's, group those together in parentheses. So all the terms without the I's in them. Going to 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. Some of you are probably starting to see what's happening at this point. Minus theta to the 6th over 6 factorial. The next one that I didn't write down over there would be theta to the 8th over 8 factorial plus, right? Okay, so those are all the terms without I's in them. All the other terms with I's in them, well, since all the terms, remaining terms have an I in them, let's pull an I out in front. So, theta in that term, minus theta cubed over 3 factorial from that term, plus theta to the 5th over 5 factorial from this term, minus theta to the 7th over 7 factorial from this term. The next one that I didn't write down would be plus theta to the 9th over 9 factorial, and so on. Well, let's think about what some other Taylor series are for functions we know. Right? The Taylor series for cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. In other words, it contains only even powers of x, right? This is actually an even power of x too. It's x to the 0, right? In fact, This is x to the 0th over 0 factorial. 0 factorial is actually 1, not 0. Okay. So you see the pattern. Every term is x to the nth over n factorial. And n is being summed from 0 to infinity, but there are only even values of n appearing in that summation. Okay? Similarly, the Taylor series for sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I'm sorry, this is not correct because I don't have the signs written here. This would be 1 times a minus 1 to some power. Let's see.
2n to the minus 1.
2n to the minus 1. Does that work? Let's see.
When you plug in 1, you get
Plug in 0, you would get
negative 1.
Wait, no, if we're just assuming that n is even.
Yeah.
Oh, yeah.
Let's
it's
just
my
forget
bad.
about
It's-
that. Okay,
yeah.
I don't care about writing it
It's an
like
even
that.
function.
There, you can figure out minus 1 to some power is going to
Yeah.
work, but you have to figure out what power it is. And I don't want to spend time doing it because I don't really care. I just care about looking at this pattern.
Yeah.
Okay? But notice the pattern, right? Alternating signs. And again, only even powers, and whatever the power is, they have the same number factorial down here. Down here it's the same pattern, except it's only odd powers instead of even powers. Okay? Well, gee, doesn't that cosine one look like this? Right? Except x is replaced by theta. So in other words, this first term in parentheses right here is the Taylor series for cosine theta. And this thing in parentheses right here, except again that x is replaced by theta, looks exactly like the Taylor series for sine theta. So this is cosine theta plus I sine theta. And that's what I was trying to prove. Right? So you see why this is true. Okay? And then that justifies how you can write this in polar form like this.
You believe me.
Okay. Well, it's not a matter of believing, right? I showed you. I proved it mathematically. You don't have to believe me. Okay, so anyway. Okay, so what we have proven is that e to the I theta is equal to cosine theta plus I sine theta. And we're going to use this so much. You know, I hate to say memorize anything because, you know, the emphasis is always on understanding, not memorization. Well, we are going to be using that so much that I think you will end up memorizing it, okay, whether you really try to or not, okay? So this is very important. Okay, well, in this expression, let's think about what would happen if we replace theta by minus theta. Okay, this is true for any value of theta, so we can certainly replace theta by negative theta. Then we'd have e to the minus I theta. That would be equal to the cosine of minus theta plus I times the sine of minus theta. Now, recall that cosine of minus theta is equal to cosine of theta. In other words, cosine is an even function. Everybody knows what I mean by an even function? An even function, if f of x is an even function, it means that f of minus x is equal to f of x. Okay? Or graphically, if I graph f of x as a function of x, it means that whatever this graph looks like for positive values of x, maybe it looks like that or something, it's going to look like that for negative values of x. In other words, if I folded it around the vertical axis, Right? The left side and the right side are sort of mirror images of each other. And cosine is an even function. And if you don't know why it's an even function, you could actually see it very easily from the Taylor series. What would happen here if I replaced x by minus x? Since I only have even powers, made no change at all. Right? So clearly, cosine of minus x is the same as cosine of x. And similarly, sine of minus theta is minus the sine of theta. In other words, sine is an odd function. Okay, and again, what I mean over here by an odd function, if some function f of x is an odd function, it means that f of minus x is equal to minus f of x. Right? You can pull the minus sign out in front. Or graphically, if f of x as a function of x looks like this for positive values of x, right? Well, whatever the value of x, like this one right here, f of x is that height. So if I go to f of minus x, the same distance to the left that this one was to the right, at that position, the function value will be the negative of what it was here. So it will be down below the axis right there. So in other words, it looks something like that. So in other words, if I look at the function over here for positive values of x, fold it over, but then fold it upside down to get what the function looks like for negative values of x. Okay, sine behaves like that. Right? I mean, you can see graphically also that this is true. For cosine x as a function of x, right, the graph looks like that. For positive values, I just fold it over, get that one for negative values. Similarly, sine x as a function of x. For positive values of x, it looks like that. For negative values of x, I fold this over, but then fold it upside down. Get that. You can also see that sine x is an odd function from the Taylor series. Right? If I were to replace x by minus x, since there are only odd powers of x, that would change the sign of every term. Right? And so it would be equivalent to putting a minus sign out in front. So anyway, that means that e to the minus I theta, I had this expression for it right here, but since cosine is an even function, cosine of minus theta is the same as cosine theta, and since sine is an odd function, sine of minus theta is the same as minus the sine of theta. In other words, this is minus I sine. I've got two equations I just put a box around. This one and this one. Okay? Let's add those two equations together. Okay, so if I add those two equations together, adding together the two left-hand sides, gives me e to the I theta plus e to the minus I theta. And on the right-hand sides, when I add the right-hand side here to the right-hand side there, the I theta there and the minus I theta there cancel, and we get 2 cosine theta. Or dividing both sides by 2, it means we can write cosine theta as e to the I theta plus e to the minus I theta over 2. I don't know if you've seen this before, I'm hoping you have, but I'm going through this in case you haven't. This is so important, and let me show you why in a moment, okay? But before I do that, let me also point out that we could similarly subtract those two boxed equations from over there. Okay, so on the left-hand side, we'll have e to the I theta minus e to the minus I theta. On the right-hand side, when we subtract this equation minus this equation, the cosine thetas will now cancel. Well, I sine theta minus a minus I sine theta, or in other words, 2I sine theta. Or if I divide both sides by 2I, sine theta is e to the I theta minus e to the minus I theta over 2I. Okay? So we have an expression for cosine theta written in terms of complex exponentials, and an expression for sine theta written in terms of complex exponentials. Let me give you a demonstration of why these are so useful. And we will be using these again and again, okay? So, again, remember them, okay? Or you will remember them eventually, whether you set out to do so or not. You can use these to prove any trig identity. Okay? And there are a lot of trig identities you probably don't remember, right? I don't remember them all either. There's lots of them out there, and some of them you don't use very often. You look them up on a table when you need them, right?
Yep.
But what if you are doing your work somewhere where you don't happen to have a table handy, right? You can derive it, and it's so easy. You can prove any trig identity in like a line or two, okay? It is so easy to do it if you use these expressions. Let me show you an example. Let's say you have cosine squared theta minus sine squared theta. Right? There's some trig identity that says what that's equal to. You probably remember that if it was plus instead of minus, the answer would be 1. Right? That's sort of the most famous of all trig identities. And by the way, you could prove that one using these expressions too. But let me show you how it works for this one. So let's just substitute these for sine and cosine. Okay, so cosine theta is e to the I theta plus e to the minus I theta over 2. It gets squared. And then minus sine theta, and sine theta is e to the I theta minus e to the minus I theta over 2I. And that gets squared. Okay, so let's square this out. We're going to get a 4 on the bottom, right, from squaring the 2. On the top, we're going to get an e to the 2I theta. Right, that's from squaring this term. From squaring that term, we'll have an e to the minus 2I theta. And we're going to have a cross term, which is 2 times this times this. Okay, well, this times this is 1. Right? Because remember, when you multiply exponentials, you add their exponents. So e to the I theta times e to the minus I theta is e to the quantity I theta minus I theta, or in other words, e to the 0, which is 1. And then we have a 2 times it because it's a cross term, right? A plus b quantity squared is a squared plus b squared plus 2ab. Okay? So that's from squaring the cosine. This one, when we square the sine, we've got a minus sign out in front, remember, so I'll just leave that there. On the top, we have an e to the 2I theta. Right, from squaring this term. From squaring that term, we have a plus e to the minus 2I theta. And our cross term is minus 2, right? Minus 2 times this, and this times this gives you 1 again. And then on the bottom we have 2I quantity squared. That's minus 4, right? Well, of course, that minus sign could be pulled up front and change this to a plus sign. So this is really the same thing. We put it all over a common denominator of 4. Right, that's what we had in the first expression. Again, those minus signs cancel, so now this is a plus sign. So now that 2 and that minus 2 cancel. And let's combine this term and this term. That would give me a 2 e to the 2I theta. Similarly, this term and this term would combine to give me a 2 e to the minus 2I theta. Both terms would have 2's in the numerator, but there's a 4 in the denominator, so I can cancel out a factor of 2 on top and bottom. So in other words, I'm left with e to the 2I theta plus e to the minus 2I theta all over 2. Well, now look back at this. This looks an awful lot like what we have here, except there are 2's in the exponent where there aren't here. In other words, this looks like the expression for cosine theta, except that theta is replaced by 2 theta. In other words, this is the cosine of 2 theta. So our trig identity says that cosine squared theta minus sine squared theta is equal to the cosine of 2 theta. Okay? You see how easy it is to derive that? They're all similarly easy. Okay? Every trig identity in the world, I promise you, is that easy to derive with these expressions right here. Okay? That's something you can easily do if you lost your table of trig identities. Right? You can derive any one of them you ever will need.
Or somebody insists on you memorizing them.
Yeah.
Well,
Other definitions aren't as
these
nice
are not
as
the
you.
things, you know, the goal is not memorization, right?
Yeah.
The goal is understanding. And hell, if you could derive it, isn't that so much
Easier.
indicative of better understanding than just having memorized a bunch of things?
Pretty much.
Okay?
I mean, in a hard science, I really don't see a point in memorizing anything.
I agree. And you know, when you're out there in the real world, you can look things up when you need them. right?
Exactly.
Break time?
This is why I like bringing a cheat sheet to your tasks. Okay? I don't care about making you memorize things.
If we know how to use it, if we know how to.
Well, and
That's
to be honest, making the cheat sheet itself is a good way to study, because it forces you to decide what's important.
Exactly. Yeah.
By the way,
Or at the very minimum, it increases your ability to represent. Which could be
remember there were such things as hyperbolic trig functions? Right, sinh and cosh, for example. I'm not going to go into this in detail to show you where it all comes from, but there are similar expressions for them to the expression for sine and cosine. All you do is leave out the i's. So in other words, the cosh of x is e to the x minus e to the minus x over 2.
Your old sign.
That is fine.
That's sinh. I pointed to
Yeah.
cosine, no, which was the wrong one. I should have pointed to this
Pay
one.
attention on that.
Just leave out the i's, right? Leave out that I and that I in the exponent, leave out that I in the denominator. Got the same expression. Same thing here for cosh. Right? Cosh of x is e to the x plus e to the minus x over 2. There are trig identities, I shouldn't say trig, hyperbolic trig identities, right, involving these hyperbolic functions as well. You can derive them in exactly the same way by using these two expressions. Okay? So again, whenever you need them. Okay?
No, that was my idea. Thank you.
So again, that's really important. Okay, I'm sorry, we got a little bit over where we probably should have done our break. So let's do a 5-minute break, and then we'll start talking about how this is applicable to waves, which will kind of take us into Fourier analysis.
Feel my mom got married.
Okay, well, you've seen lots of examples of infinite series, right? We just talked about, for example, Taylor series, right? And in the Taylor series, you write a function, some function f of x, as a power series, right? In other words, each term in the infinite series has x to some power, right? There's typically a constant term or an x to the 0 term. There's an x to the first power, an x squared, an x cubed, an x to the fourth, and so on, terms, right? So x to the n, we're summing over n. There's another kind of series that we can write other than a power series, like a Taylor series, called a Fourier series. And in a Fourier series, we're going to write f of x as a sum, and it's going to be an infinite sum in most cases, of cosine and sine terms. Or equivalently, by the way, since we know we've just seen that cosine and sine theta can be written in terms of complex exponentials, that means that we can also write our Fourier series, and instead of involving sines and cosines, we can also write it in another form that will involve complex exponentials. Okay, so we can do it either way. We'll first of all talk about how to do it with the sine and cosine terms, but then later we'll come back to how we can rewrite that in terms of complex exponentials. Before we actually write the series, though, it's going to take us a little while before we get to the point of actually writing this down. Let me point out there are some restrictions on the functions that can be written this way. There are some more detailed conditions that we'll talk about later, but for now, let's say almost any function f of x that is periodic. Okay? What do we mean by periodic? If f of x plus L is equal to f of x for any value of x, then f of x is periodic with a period equal to L. Right? If, in other words, we add L to the argument, the function has the same value that it did before we added the L to the argument. Okay? So just some examples of what I mean by a periodic function. Let me just give you some sketches of f of x versus x for a periodic function. A sine function is periodic, right? It keeps repeating itself over again. For, right, this is equal to L. And so if I pick a particular value of x, like maybe this one right here, then adding L to that, I'm sorry, that's not L. Actually, yeah, that is. Okay, so x plus L, or if x is equal to this value right here, then x plus L is right there, and you can see the height of the function right here is equal to the same height right there, right? And similarly, right, if I use this value of x, well, adding L to it gives me this value right here. Okay. But it doesn't have to be a sinusoidal function. It could be a function that has a different shape. Right? It could be a sawtooth or triangular wave, something that's shaped like that. again, this would be the value of L right here. And it could be something with a more irregular shape to it. Right, something like that. Right? Any sort of periodic function. It could even have discontinuities in it. Right? It could be something like this. Right? As long as the pattern, the shape repeats itself over and over again. Okay? So all of those are periodic functions. So, and in a way you can think of sine and cosine as sort of the most simple periodic functions. What I'm claiming is that we can get periodic function of any other shape that we like by adding together appropriately chosen sine and cosine functions, and we'll see how to do that. Yeah?
Could you also write tangent or a function that have asymptotes and come back up on?
Yeah. Okay. Again, we'll talk about, it's an almost any function. There are a few conditions which we'll talk about later, okay, as to whether we can do this and whether we can't. But anyway, since we're going to be concentrating a lot on sines and cosines, it's worth maybe thinking about some of the different ways we can write sines and cosine functions, and maybe we can tie this in with concepts like wavelength and period and so forth. So let's think about a function like, for example, let's consider the function f of x equals a times the sine of kx. Okay. We often also write this as a times the sine of 2 pi x over lambda. Lambda, of course, is the wavelength. And k is the wave number, as it's called. And you can see by comparing these two different ways of writing this function that k has to be equal to 2 pi over lambda. So the wavelengths and wave number are related by that formula. And of course, if I draw a graph of this function f of x as a function of x, it's going to look something like this. And lambda, the wavelength, probably sounds pretty much like what I talked about for L over here. Okay? I'll clean up this notation and talk about how these things compare in a moment. But we're looking at a function of x right here. And for example, this might, look like a snapshot of a traveling wave at some fixed value of t, some fixed time. I remember in Physics 223 you learned about traveling waves, right? Like a wave on a string, or a light wave, or a sound wave. A snapshot of the wave at a fixed moment in time would show that wave as a function of x, and it might look something like this sinusoidal wave. But then it moves along with time. Maybe it's moving to the right, for example. But again, if you freeze it in time and look at a snapshot, you can write it just as a function of x. And you could write it in this form up here. And of course, a is the amplitude, right? Which is half the total height, right? From the origin to the peak, in other words, that distance. But sometimes we also might want to be looking at functions of time that are similar, in the sense that, again, if we look at a graph of f of t as a function of t, it could again be sinusoidal. this could be describing simple harmonic motion. Okay, for example, if you have a mass on a spring, right, here's the mass, here's the spring, the other end of the spring is, let's say, connected to the wall, and let's say you pull the mass to the right, you extend the spring and then let it go. You know it's going to vibrate back and forth, and let's assume there's no friction, right? That means it's going to vibrate back and forth forever. And if you graph its position as a function of time, it might look something like what this graph shows you, right? And so we could write this as A times the sine of omega t. A is the amplitude, which is again the height, or half the total height of the wave. Or we could similarly write it as A times the sine of the quantity 2 pi t over capital T. Capital T is the period, which is this time right here on the graph. It's the time it takes for one complete cycle of the motion. And so you can see that that's similar to lambda over here in this picture. In fact, if we compare these two situations with each other, except for some changes in notation, everything's exactly the same, right? Here we're looking at f as a function of x. Here we're looking at it as a function of t. The k, the wave number, that multiplies the x in this way of writing it, is analogous to the omega in this, when we think of it as a function of t, and I should add omega to the list here. Omega is the angular frequency. And comparing these two ways of writing f as a function of t, you can see that omega is equal to 2 pi over the period capital T. And notice that that's comparable to this, right? K there is replaced by omega there, and lambda there is replaced by capital T there. So let's add to our list lambda. In fact, you can see it here too. If you take this expression and you replace x by t and lambda by capital T, you get this expression over here. So really these are two identical situations except for the names of the variables that we're using in the equations, right? Mathematically, these are essentially the same thing. So we're going to describe things that can be applied to either of these, okay? And so we will use the following terminology. We'll be calling our function f of x, but remember, x could be replaced by t in everything we're going to do. And we will use L, we'll call L the period, but that period, again, this can be either the period capital T that we used over here when we're thinking of our function as being a function of time. If we're thinking of a function of a spatial coordinate f of x instead, then the thing that's analogous to the period is, of course, the wavelength. Right? So if we're looking, the thing that we're going to call our generic function f of x, we're going to say it as a period L. But in the terminology we've used here, what that period really then means, of course, is the wavelength. But we could also be thinking of a function of time, in which case our period is the period of time that it takes for our function to repeat itself. Okay? So again, these are analogous. Okay? By the way, notice that sine x and cosine x have a period equal to 2 pi. Okay? Because the sine of x plus 2 pi is equal to the sine of x. Right? And that was the definition we gave right here for the period. And the period of sine of, well, we said right here, the period of sine of 2 pi x over L. I'm simply using L instead of lambda in that expression, is L. And so the period of sine x, well, we could write sine x as 2 pi x over 2 pi. Right? The 2 pi's would cancel and just give us sine x back again. So if you compare this to this, you can see, again, that the period is 2 pi, which is, of course, exactly what we said right up here. And the same thing would be true of cosine, of course. Right? So in a Fourier series, this is again an infinite series, and let's say the first term, maybe I shouldn't call it a first term because it's not necessarily the first one we'll write down, but I'll write this down in a minute and you'll see what I'm talking about. I'll identify it then. Sometimes we call it the fundamental term. The first term has the same period as the function f of x that we're trying to write the Fourier series for. Right? We're going to be writing f of x as a sum of sine and cosine terms. So, for example, if our f of x as a function of x, maybe it looks like a triangular wave like that, for example. Right? That has a period we'll call L. Okay? So, in other words, our f of x in this case would be a sine term, let's say, with a period of L. In other words, the sine of 2 pi x over L. Right, that will be the first term. There's going to be some other terms here to come that I'll write in a moment. But of course, what would sine of 2 pi x over L look like? It would just be a sinusoidal function, but it would at least have the same period as the function that we're trying to write the Fourier series for. All the later terms have to do is, so that term is called the fundamental, right? A sinusoidal, and it could be a sine or a cosine. I just wrote sine in this case because it started at the origin, and I know sine starts at the origin and cosine doesn't. Okay? And then there are going to be subsequent terms which are sometimes called harmonics or overtones. And this terminology is especially used when people talk about sound waves, especially in the context of like music, for example. But a harmonic or an overtone, each of these has a period L over n for some integer n. In other words, they have shorter periods than the fundamental term. Right? So there will be a sum of other terms that involve signs of, let's see, if the period is L over N, then I'm going to replace L by L over N here. So in other words, there will be terms that look like the sine of 2 pi nx over L. N will be summed from, well, n equals 1 would give me this term, which I already wrote separately. So let's say 2 to infinity, since the n equals 1 term is already looks like that. And of course, there could be some cosine terms as well. Again, we'll write down a more general way of writing this in just a moment. But I'm giving you an idea of what it might look like. And basically, these subsequent terms, the terms with the smaller periods, basically, when we add those into the fundamental term, these change the shape of the wave. From a sinusoidal shape to a shape maybe like this, or whatever the function, whatever the shape of that function is on the graph. Okay, so the first term is going to provide something basically of the right period. Notice that the frequency, I'm going to use this terminology, the terminology associated with a function of time rather than distance here, because that's pretty typical when we talk about this. Notice that the angular frequency and the period are inversely proportional to each other. So if our periods of our separate terms in our Fourier series involve L over n for integer values of n, we could say, just as easily, we could describe it in terms of frequency, right? Our frequency for our first term would be a value of omega, which is equal to 2 pi over t, the period. And then our overtones, or our harmonics, would have periods of L over n, or frequencies of n times omega. And if omega was the frequency of the fundamental, then these would be integer multiples of that same frequency, right? Again, inversely proportional to period. Period has the L in the denominator, or the n in the denominator. This has the n in the numerator. And again, these change the shape of the wave. We can also add a constant term. And basically, that just lifts up the function. For example, let's say instead of a function like this, that we were trying to write the Fourier series for a function like that. Right? Looks just like this one, except it's raised up. Right? This one started at 0. This one, I'm sorry, I should have started at a similar place in it. I should have started it like that to look. In other words, take this one and just raise the whole thing up, right, by a certain amount. So whatever this constant is right here, if I have the Fourier series for this way, I would simply have to add that constant to it to get the Fourier series for this one. That's going to just move the whole thing up. This is still a periodic function, so I still should be able to write a Fourier series for it. So I have to allow the ability of I have to allow for a possibility of a constant term in my series in order to be able to write a Fourier series for a function like this. Okay? So anyway.
And that's just put onto the end of our function there, plus some constant.
Yeah, well, this is why I said something a moment ago about maybe I shouldn't have called the first term, because in the expression for the Fourier series that I was just about to write down for you, I'm actually going to write this constant term first. But I'm saying conceptually, in a sense, this is maybe the first thing you'd want to do to try to match your function, right, by choosing some sine or cosine functions to do it. Okay? Okay, so anyway. our basic expression for a Fourier series is going to look like this. Okay, so I'm kind of put together what I said right here. So here's our constant term. I'm going to call it A naught over 2. And you might say, why did I choose that name? Well, we'll see in a moment. Okay? So this would be A naught over 2, for example, for this function right here. Okay? Plus A1 times the cosine of 2 pi x over L. Well, except for the fact that I wrote down cosine instead of sine, that looks like this term. And I didn't put a coefficient in terms of this because I was being a little bit sloppy here when I wrote it. I was just trying to give you an idea of what kinds of sine or cosine terms went in here, but there could be coefficients in front of them. Okay? So this is a cosine term that has a period of L. Okay? Is this function right here. And an amplitude of A1. Another cosine term that has an argument of 4 pi x over L. Well, that looks like an example, except that it has cosine instead of sine, of a term like this where n is equal to 2, right? There could also be a similar term when n equals 3. That would be a cosine of 6 pi x over L. Notice in front of each term I put a coefficient, an amplitude multiplying that term, which is a sub n, where n is whatever the integer is that appears there, right? So in the 6 pi x over L, it's like this with n equals 3, so I've called the coefficient A3. And there could be a similar A4 term times the cosine of 8 pi x over L. And higher values of n. And there could also be some sine terms, right? I said there could be both cosine and sine terms. I'm going to call the coefficients of the sine terms b's instead of a's. Okay? So b1 times the sine of 2 pi x over L. That again looks like this term here. I've just put a coefficient out in front. There could be a b2 times the sine of 4 pi x over L. That looks like this term here with n equals 2. Right? Similar term with n equals 3 would be b3 times the sine of 6 pi x over L. And so on. The next term would be b4 times the sine of 8 pi x over L. And so on. Right? Or in other words, if I write this in summation notation, we'll keep the constant term A naught over 2. Again, you'll see later why we write it that way. And then let's write a summation notation for the rest of these. I can write a sum from n equals 1 to infinity of the quantity a sub n times the cosine of n pi, or 2 pi rather, 2n pi, or 2 pi n x over L, plus b sub n times the sine of 2 pi n x over L. Okay.
Wait, that n should be in there? Inside the angle?
Yeah. Because remember here,
Oh.
it's all I've done here is this looks like this with n equals 1. So I could, if I'd started the sum at n equals 1, I didn't have to write that term separately because now it would be included as the n equals 1 term in that summation. That's all I've done. Okay? So again, remember the n is there because we have a period of L over n for the nth term in that sum, or equivalently a frequency gets multiplied by n, right? So that comes in the numerator. So this is our general expression for a Fourier series, it kind of does what we talked about over here. But of course, what we haven't talked about yet is how do we find the a sub n's and b sub n's? Right? How do we find those coefficients of each term, including the a0, that's the constant term out in front? Right? That's really the hard part of writing a Fourier series, is how to find those coefficients. Right? This is going to be the general form otherwise. Well, we're out of time now, but this is what we'll pick up with next time. Well, actually, next time we ever test. So Wednesday, we'll start talking about this. And since homework 5, originally when I gave it to you, I said it'll have a due date of Wednesday, but we haven't talked about everything we need yet for you to finish that homework. So we'll postpone that due date until a week from Monday. Okay, a week from today of our test.
So much time.